this NARS tutorial. This tutorial will consist of two parts. I'm Pei Wang. I'm going to give the first part, which is the conceptual design of the system. And after that, Patrick Hammer of the development NARS team, as well as helped by the other team members, is going to introduce the code to you. The material, as I want to mention, first, this PowerPoint presentation is already linked to the conference schedule here. Okay. Probably slightly different from what I'm going to show, but it's basically the same thing. For the conceptual design, most of the stuff we are going to talk about today already published, can be accessed from my website. The easiest way to get here is just Google my name, and then you go to my website at Temple University, then you follow this publication link. There are about 60 papers on different aspects of this project. And also there are two books, which are unfortunately not online, but all the other papers are there. And then Patrick will mention the material, the documentation and so on of the code. So let's start from the very beginning. It's well known that a lot of difference in the field is caused by a different understanding about the concept of intelligence. So to mainstream AI, intelligence is typically interpreted as a collection of problem-specific and domain-specific functions. For AGI people, they typically take intelligence as a general-purpose capability, and they should be treated as a whole. Even though that's more or less the consensus of the AGI community, we still actually define our task of research very differently. As you probably have already seen. If you haven't, you will see it in the next 3 days. So I will start with our understanding. So the whole work, a lot of discussion will go back to this very paragraph. That is, intelligence in our work is understood or interpreted as the capability of a system to adapt to its environment and to work with insufficient knowledge and resources. So there are two components in this working definition or our understanding of intelligence. One is adaptation, which is not very controversial. Right? I think most people agree. But the other one is probably the one that actually distinguishes our work from many other works in the field. That is a so-called assumption of insufficient knowledge and resources, sometimes referred to as AIKR. What does that mean? That actually means three things. One is to rely on finite processing power in terms of, say, number of processors, processor speed, the amount of storage capacity, and so on. Okay? You have a finite amount. And second one is the system must work in real time. Actually, by real time, we mean something slightly different from the field. In the field of computer science, real time typically taken to mean something like you have a deadline, right? In our system, actually, we mean more than that. We mean for most of the tasks, the requirement is to solve it as soon as possible, with different levels of, sense of pressure or urgency. Later we'll see more details. Okay? That's what we mean by real time. And finally, we want the system to be able to open to unexpected tasks. Roughly speaking, it means two things. Of course, every system can only perceive or accept tasks or new information in a certain format, that's for sure. Okay? But our definition requires that, yeah, you can say that there's a certain format you have to be in to be accepted by the system. But any content should be acceptable. Which means several things. For example, it means new information can conflict with the system's current belief. The system cannot be killed by that, or crashed by that, or contradiction, or inconsistency will be allowed. Okay. Also, the new questions or new problems may be beyond the system's current capability, or beyond its current knowledge scope. You cannot just say, oh, I don't know. That's not something I have been designed to solve. Okay. The system has to try to work on those problems. That's what open means in this context. So that's very roughly speaking, at a very high level, philosophical level, what problem we want to solve. We want to build a system which satisfies this restriction. And then, on the technical side, the top level assumption or decision we make is to build a system in a framework of a reasoning system. Okay. This is not a new concept at all. I think everyone here, or almost everyone here, know what a reasoning system means in the field, which typically has the following components. It uses a formal language to represent its knowledge. It uses some kind of semantic theory to define what meaning and truth is on this language, so that we will understand how to use the language. Then there is a set of formal inference rules, okay, which derive new things from given things. And this array, typically put together, is called a logic, in the broad sense of the word. Then what? Then when we say we implement a logic into a system, we mean more than that. It's a logic plus something. That plus something includes at least a memory structure. Okay, we need to be able to remember the given knowledge and so on. And a control mechanism, which will decide in each step which promise to use and what inference tools to use. Those things put together is called reasoning systems. In a very broad sense. So why to use a reasoning system? This is a controversial issue. Okay. I think many people now already think about, oh, reasoning system again, now this is already bad. Okay, now it's a neural network, which is the one that's promising. But I'm going to argue not only today, but also tomorrow and later, okay, whenever I have a chance, I will say, it's too early to say, okay? Reasoning systems still have some very important advantage compared to the other things, including neural network. One thing is it's domain independent. Okay, logic is not designed for any specific problem. That's easy to understand. And also, this is a little bit controversial. Many people say logic is too rigid. Okay, later I will show you when you extend it properly, a logic or a reasoning system can have a very rich expressing power. At least it should satisfy the requirement of AGI. And then another important feature is, you see, when you say your system is following a logic, that basically means every step you need to have a justification. Okay? An inference rule is not just a rule. It's a rule with a justification. Okay? It's something correct or valid to do. Not an arbitrary step. That's very important. But that sounds rigid. There is another aspect of a reasoning system is the flexibility. That is, even though each step needs to be justifiable, needs to be rigid, yes. But how you combine those steps together, it can be very flexible. So put together here, the vision is kind of intuitively speaking, something like we try to analyze all types of reasoning into basic steps, and we are going to define all those steps as an inference rule. And we are going to use their combination to reproduce all types of thinking process. Okay. That's kind of like the intuition. And let's see whether we can do it. But just from my previous discussion, some of you may have already seen a deep contradiction between what we want to do and how we try to achieve it. Why? Because under the assumption of insufficient knowledge and resource, it means what? It means there's no way for you to guarantee absolute correctness or absolute truth in your system. Okay? Everything can be challenged by future experiments, can be wrong in that sense. And also, you don't have enough time to go through all possibilities. So in this sense, everything will be uncertain. You will see, yes, that's indeed the case. On the other hand, logic traditionally is interpreted as a process which goes from truth to truth. If you have no truth to start with, and you cannot guarantee the truthfulness of your conclusion, how can you say you are following a logic? So there is actually a philosophical contradiction between our two assumptions, okay, our goal and our strategy. So the solution to that also is philosophical. I have tried, with the help of some other people, to redefine or reinterpret the concept of valid, what is valid or what is rational, on the foundation of available knowledge and resource. I will say that my conclusions are valid with respect to or relative to what I know and what resource I have at the moment. So that's the basic idea. So you'll see I have already given up absolute truth or absolute optimum. In return, what I try to obtain is I want the system to be general, to be adaptive, to be flexible, and to be robust, and to be scalable. So that's kind of like the philosophical discussion. I don't want today to be pure philosophy. I know you don't want that. So, but I have to mention that because that's the foundation of everything else in the following. Okay? So from this slide, I'm going to begin to talk about technical stuff. But given the complexity of this project, there is absolutely no way for me to cover all or most of the technical material. I will just talk about the basic. Okay, for the rest, as I said, I have papers, I have books, and we have 3 more days. We will be here. Okay, otherwise, welcome to talk to me or to my team members about the details. But here, I will talk about the basic. So, yeah, I said I use a formal logic, which means a formal language. This formal language, the smallest unit is what I call a term. A term is just, in the simplest form, it's just a word, okay? Or an ID, identifier within the system, which will be used as a name of a concept. Later I'm going to define what a concept means in the system. But now we just use it intuitively. Then terms are related to each other to form statements. A statement in the system has a subject predicate format, and these two terms are related to each other by a copular. And see, formally, S is the subject term, P is the predicate term. This arrowhead is a copular I call inheritance. Intuitively speaking, it means the subject is a specialization of the predicate, and symmetrically, the predicate is a generalization of the subject. Concrete example, also you can put it in a graphical manner. Okay? You see each term is a node, and a copular is a link from the subject to the predicate. There, the direction matters. Okay? You see water is a type of liquid. So liquid is a more general concept compared to water. Water is a special case. So that's the intuitive meaning. And this copular, what I call inheritance, is formally defined by its two properties. One is reflexive, one is transitive. Reflexive means from every term, there is an inheritance relation to itself. Yes, water is water. Transitive means, well, if A is a type of B, B is a type of C, then A is a type of C. Well, it's trivially true. Okay. Then based on those trivial definitions, we can define first idealized truth value, that is a binary truth value, on the statement. First, we introduce the concept of experience to the system. Just like every reasoning system, you cannot get something from nothing, right? You have to start with some background knowledge or given premise, whatever you call it. In this system, it's called experience. Later, we'll see why. So it's just a set of given statements. Then based on that, I define the concept of the system's beliefs, which is the transitive closure of the experience. Intuitively speaking, that's basically what the system is told, as well as what can be derived from the given just by transitivity of the relationship. And there is only one relationship allowed at this stage, that's inheritance. So you cannot be simple. What is true? Well, a statement is true. There are two situations. One is in the beliefs, which means it's either given or can be derived from the given. Or it's a tautology. That's true by definition. Otherwise, it's false. So here I'm using a closed word assumption, which is a common thing to do in AI as far as you say you only want a binary logic. So it's also pretty simple. Then we begin to define two new words, which are used slightly differently compared to many other systems, even though the intuition is still there. I'm going to define extension and intension of a term. Formally speaking, the extension of a term, well, let me show you the picture, which shows it much better. Okay? So if T is any term here, its extension is a set of terms that there is an inheritance link from that term to T. That is, there are specializations. T's specializations, all the terms that's more special than T. Semantically, intension are the generalizations of T. That is, there is a link from T to those things. And T itself, by definition, is in its own extension and intension because of the reflexivity. Then there is a trivial but important theorem that can be proved. That is, there is an inheritance relation from S to T if and only if the extension of the subject is a subset of the extension of the predicate. If and only if the intension of the predicate is a subset of the intention of the subject. Okay, this is just transitivity. But why this is important? Because this is the foundation of extending this logic from a binary logic to a multi-valued logic. Okay. From my previous description, you should have already guessed. In this system, in my system, there is no absolute truth anymore. But on the other hand, I won't say everything is as good as everything else. So truth will be a matter of degree. Okay, just like many multi-value logic. But there is a common problem about multi-value logic, for example, fuzzy logic. That is, what that number means. To make it very clear what that number means, what I'm doing, you see here, is I identify one of the statements I want to define on the left-hand side to the other two in the middle on the right-hand side, which are subset relations in set theory. I say they are the same thing. But a subset relation can be very naturally extended from binary to multi-value. Okay? A binary subset relation is basically saying, okay, A is a subset of B, it means 100% of A is in B. If I want to make it 80%, everyone understands what I mean. Okay, 80% of A is in B, the other 20% are not. So in the following, I'm going to do my trick for this logic. So I'm going to piece by piece introduce what the evidence for a sentence to be said to be true, and what is the evidence for a statement to be said to be false. According to the previous theorem, okay, then you see it will naturally lead to a multi-valued logic with a clearly defined semantics, what that number means. So for a given statement, S is a type of B, I will say everything in a common subset, common extension or common intension of the two terms are positive evidence. Negative evidence are the terms that in the extension of the subject but not in the extension of the predicate, or in the intension of the predicate but not in the intention of the subject. Again, it sounds complicated. Let me show you the picture. So we're talking about this relation in the middle. If I can find something which is both in the extension of S and in the extension of P, as far as this thing is concerned, the extension of S is indeed included in the extension of P. Be careful here. I'm not talking about the whole extension. I'm talking about one instance of it. The same thing for intension. You see in the system, intension and extension are perfectly symmetric to each other. Okay? But for the negative evidence, if something is in here but not in here, of course, as far as this one is concerned, this subset relationship is not true anymore, which means equivalently, this inheritance relation is not true anymore. Okay? So based on that, not only I can define positive and negative, I can measure them. In a simplified situation, I simply just use the size of the set involved. So the amount of positive evidence means the size of the common extension and the common intention together. The total amount of negative evidence, is this part, or the kind of the red thing, you just count them, okay? That's negative. The green things are positive, and you get a total counting value. Okay? Then if you add them together, that's the total amount of evidence. According to what, of course, or according to the system's experience. Okay? Be careful. This is just the definition of evidence. This is not how it is actually calculated. That's a different story. Okay? Here, let's go back to see what we have done. First, we define what is experience. We use experience to define truth value. Then we use truth value to define extension and intention. Then eventually, we define for arbitrary statement. Given that experience, how much evidence you have, positive, negative for a given statement. Then finally, the last step, we use the amount of evidence to define truth value. What makes this system different is not only is a multi-value, it actually uses two numbers to represent the truth value. Many people say, oh, one number is already too complicated, you use two. Well, I have enough recently that I will show you. We use two numbers to represent a truth value. And both of them are real numbers between 0 and 1. The first number is called frequency. It should look very familiar. Is the proportion of positive evidence among all evidence. Like what I just said, okay, 80% support, 20% against. So frequency is 0.8. Okay? But be careful, this is not probability. Because probability is relative frequency take limit, okay? I'm not taking limit. So it's just the current proportion of positive evidence among all evidence. And this evidence may come from extension, may come from intention, as I just defined. But still, this looks pretty natural. And the second thing, the second component is probably most unique in terms of the semantics of the system, is what I call confidence. Okay? This same word has been used by several different theories like statistics to mean slightly different things. So here, what I use it for, this W is the total amount of evidence divided by total amount of evidence plus 1. Y plus 1. Well, one story, okay, to make it short, actually it doesn't have to be plus 1. It can be plus, 2 or 3 or 1. But the intuition is we need a measurement to measure how much you know about that thing. Okay? Traditional theory, including probability theory and fuzzy logic, have a problem of cannot really say, I don't know. You see, probability 0.5 doesn't mean I don't know. And here we have a mechanism to really say, I have absolutely no idea. That is confidence equal to 0. Okay. You see, this W is how much kind of like evidence you have seen. If you haven't seen anything, confidence is 0. If you have seen one piece of knowledge or one piece of evidence for that statement, you see, it's 1 divided by 2, it's 0.5. You have see 2 of them is 2 divided by 3 is 2/3. And then it will be 3 divided by 4, 4 divided by 5. It will never reach 1. So basically, my current interpretation in my publication is basically say, what this measures is what you know at the moment compared to what you will know in the next moment after you get one piece of new evidence. Okay? So the next moment, you will always know more than the current moment because you get one piece more. But if you already know 1 million, and that difference will be very small. 1 million plus 1. Okay, is basically the same as 1 million. But 1 compared to 2, that's very different. So you see, the intuitive meaning of this measurement is to measure how the system will be sensitive to new evidence. The more you already know, the less sensitive it will be. But there is always a chance for you to get new evidence. So mathematically speaking, this formula actually indicates why I call my system non-axiomatic logic. That is, no absolute truth. Everything can be modified. It will become harder and harder and harder and harder if you get more and more and more and more evidence. Okay. So graphically speaking, then now we can add a weight value to the link. It just this weight value is actually 2 numbers as a pair. So now we can summarize the semantics of NARS, which is very unique. I say this system has an experience-grounded semantics in the sense that everything, semantically speaking, is defined with respect to the system's experience. So you see the truth value of a statement is defined by what? By available evidence. It's about how much you know about this thing. It's not defined with respect to a fact, which is traditionally how truth is defined in flexible model theory. Okay? True means match the reality. Here, there's no such a thing as reality. What you have is your experience. You compare your belief with your experience to see to what degree they fit into each other. The same thing about meaning. Traditionally, in model theoretic semantics, the meaning of a word is its reference in the world. Okay? There is an object where this term or this symbol is just the name of that object, and that object gives this symbol its meaning. No, that's not what this system does. This system, the meaning is what is defined by nothing but the extension and intension, which I just defined, of a term, which is the experience relation between that term and the other terms. So what this bottle means depends on how much I know about it. Okay? It doesn't really determine by what it really is. So it sounds simple, but if you think about it, there are several important implications which make the semantics fundamentally different from the semantics which is dominating the current research. First, you'll see both truth value and meaning are subjective. They're not objective. It depends on which system you're taking. Second, both of them change over time because what? Because experience, by definition, extend over time. Okay? A system always gets new experience, and those experience, by definition, is going to change the meaning of the terms involved and the truth value of the statements involved. Okay? So objective or stable things, they're special cases. Changing things, subjective things, they're normal. They're the normal situation. And also objective is relatively speaking, or stable belief, yeah, you can have them, but they're relatively speaking. So this is very, very important. That's again the foundation of everything else. Of the following. Mm-hmm.
So if I understand right, would it be fair to say that NARS uses procedural semantics rather than declarative one, where the meaning is based on the statements in which things occur, and the only kinds of statements your logic allows are specialization, generalization?
Not really. Well, it's related to later. I think I hope later I will explain the difference. But yes, there is some relation to what you said. Yes, but not exactly. Later we'll see it's not just specialization and generalization, and also not only procedural, and also it can be declarative. So that's how truth value are defined. Okay, how they're actually produced in the system. Of course, two sources. One is the input. Okay, the given you have to of course provide the initial truth value. By you, I mean the user or the designer. Okay. But it will be produced according to the semantics. For example, we're experimenting using existing knowledge source like WordNet, hook it up with NARS, and provide information to NARS. WordNet doesn't come with truth value at all. It's just binary. Well, we can use some default value. Okay? Or if you already have statistics, we can convert the statistics into truth value in a certain way. Okay? So it can come from somewhere. And also, all the inference rules later we'll see is going to take premise which is true to a degree, which will generate the conclusion of cause is also true to a degree. Where those numbers come from? Well, they come from a bunch of truth value functions designed by the designer, but it's designed according to the semantics I just introduced. So you see, again, remember in the following, when we talk about truth value in NARS, don't think about the reality. Think about what the system knows about that thing. Okay, that's what this is all about. So truth function design, actually I also try to use probability theory in the first place because that's the most natural choice. But pretty soon I realized that it's not going to work. And so I use something else. Okay. The current approach is basically to treat the truth value in the system as an extension of Boolean matters. And Boolean value is just 0 or 1, right? We are going to treat 0 and 1 is an extreme case of the values I'm using, which is between 0 and 1. Okay, that's pretty natural. So we are going to start with Boolean value. Basically, we are going to study the boundary conditions first. So what if it's extreme, okay, 0 or 1? Then we are going to analyze the relationship between the premise and the conclusion according to the semantics I just introduced. Then we are going to build the Boolean functions among the variables involved, data was the example. And finally, we are going to extend those Boolean values, Boolean functions into real number functions. You'll see that Boolean functions basically are built by 3 operators, right? Not, and or. And I'm using this very simple treatment to extend them from Boolean to real number. Okay, those functions have been used by many systems, but with different semantic interpretation and justification, which in NARS we are doing the same, but we interpret them differently, which I'm not going to talk about in detail today. Okay, you can see my publication for details. But anyway, let's see concrete example. The simplest rule is the deduction rule. You see, if M is a type of P to a degree, S is a type of M to a degree, then S is a type of P to a degree. This is nothing but transitivity extended from binary to multi-valued, right? So according to this analyze, I built the following function, which is first Boolean, then extended into truth value according to the way I mentioned. Okay. I'm not going to explain the detail why that's the case, but intuitively speaking, think about it, it makes sense. So this is a concrete example. You see that this 1 and 0.9 are the default truth value. If you tell the system something without saying anything specific about how true it is, the current default value is 100% positive. Confidence is 0.9. Why 0.9? Why not 9.5? Well, it's more or less arbitrary, but not completely not arbitrary. Okay? But anyway, that's the current default value if you don't say anything. Then if we believe, if you tell the system a bird is a type of animal to that degree, and the rabbit is a type of bird, the system will derive rabbit is a type of animal to a certain degree, you'll see that confidence level is lower than the premise, which again is pretty natural. Okay? If you have something derived from something given, the derived things are less reliable compared to the given things. But frequency is still 100% because there is no reason to doubt about the conclusion. All the positive evidence given are positive. So the graphical representation, I omit the weight value. It's just kind of like, again, if you have a link from S to M, from S to M to P, then you build a new link from S to P. Actually, everything in my system can be explained as graph operation. Okay. Paul may like that, but later you will see the details are different from sigma and other graph-based representation. Okay. But there is such an interpretation. Deduction is trivial. Induction, this is probably the most interesting thing in this system. That's actually where it starts. Let's see this pattern. Again, another thing I don't have the time to talk about in detail is the formal language I use and the format of the rules I use are actually much closer to Aristotle's logic than first-order predicate calculus. Okay? Which may sound wrong because most logic textbook will tell you otherwise. But I have a lot of evidence that I can show you if you want. Actually, Aristotle's logic is a better starting point if you want to do human reasoning, not mathematical theorem proof. Okay? Mathematical logic is not wrong, it's built for something else. So, Aristotle logic, one important feature is it uses syllogistic rules. That is, two premises must share a common term. And the conclusion is a relationship between the other two. So we have already seen that in deduction, and here you see that's the same for induction. But induction, the difference is the direction of the inheritance. You see here you have a common term play the role of subject in both premises. And then what you're doing is you're building a new relationship between the two predicates. Some people may already say, oh, if that's the case, it should be symmetric. Yes, it actually is symmetric. Okay? So there is also a conclusion from P to S, which I'm just omitted in this description to make things simple. Okay? And before I talk about that, let's jump to the example. Swan is a type of bird, and swan can swim. Can you say bird can swim? Every textbook tells you, no, you cannot say that. That's a fallacy. That's true if you are using binary logic. You see, in this logic, what did it say? It just basically says that swan piece provide a piece of evidence for the conclusion that bird can swim. Because that conclusion is indeed valid as far as swan is concerned. Okay, I'm not talking about, once again, I'm not talking about all the birds in the world. I'm talking about the birds I know, which happen to be, at the moment, to be swan by itself. Okay?
So how does that change if you've got a few birds you know about that are swimmers?
Two more slides, you will see that. Okay? This is another important thing. For this conclusion, I only take the premise into account. Let's assume there is nothing else in the system. Okay? Of course, in reality, that's not true, but we will see that later. For this step, this truth value is built exactly according to the semantic I just introduced. Okay? If this is true, then this is one piece of evidence. If this is true, this is false, then this is one piece of negative evidence. The previous one is positive evidence. That's exactly what these two equations tell you. And then you convert that into truth-value relationship, that's what you get. So compared to deduction, you will see inductive conclusion is never very strong. If you do just one step of induction, the conclusion by definition, the confidence will be lower than 0.5. Why 0.5? Is 1 divided by 2. Okay? W equal to 1. Then W divided by W plus 1 equal to 0.5. But in reality, because your premise is not perfect, what you get is less than one piece of idealized experience or evidence, so it will actually be less than 0.5.
Are you using 0.45 as an estimate because it's less than 0.5, or you're using
I'm using those functions to do the calculation, and the functions are built according to the semantics, built according to how truth value are defined. Okay, the detail of the function, you can read my paper. But that's the idea. I hope today you just get the idea will be enough. Okay, no way for us to talk about the detail of the functions. Semantically, we have abduction. Here is, again, you see that familiar pattern. Now the common term, the common property, or the common predicate of the two premises. Let's see the example. What you want to decide is whether Gao is a type of seabird. What you know is a property of seabird, that seabird tend to be able to swim. And Gao happen to have that property. By that alone, what can I say? You cannot say Gao's a seabird for sure, you cannot. But that gives you a piece of evidence to believe it. Okay? At the same time, for example, if you know birds typically flies, a penguin does not fly, it gives you a piece of negative evidence for penguins to be taken to be birds. But it's not a final conclusion, it's just one piece of evidence.
Does it give you the reciprocal at the same degree?
Actually, if you see this, you will see that positive evidence are symmetric, but negative evidence are not. Yeah, we can talk about that later if you're interested. And then we answer that question. What if you have a whole bunch of evidence from different sources? Yeah, we merge them together. Okay? That's what this revision rule does. And the function of the revision rule, you will see that it's basically a way to handle, you can call it evidence accumulation, or you can call it contradiction resolution or something like that. It's basically you have the same thing, you have two different truth values. In many systems, this is not allowed at all. In this system, it is, as I said at the beginning, it's an open system. Okay, you can contradict. But here, contradiction is interpreted as you have evidence from different sources which support different truth values. As far as we can assume those evidence indeed come from different sources, you see in the conclusion we do nothing but add them together. Okay, it's accumulation. So if you convert this relationship into a truth value relationship, you'll see that frequency is basically a weighted average. So what this system does, I can tell you that this number, this 0.62, actually comes from two pieces of positive evidence. Okay? So this is actually a situation you have two pieces of evidence which tell you a bird swim. One piece of negative evidence tell you a bird cannot swim. When you put them together, you will see, oh, maybe 2/3 of my evidence support bird swim, which means 1/3 does not, or against that. This conclusion confidence level is higher than both of them. This actually corresponds to 3 pieces of evidence, which sounds pretty easy. So you can say that in a sense, in this system, it also does statistical reasoning. But a key difference is it does it in an incremental manner. It does not collect all the data, then you run statistics, say what's a percent. No. It takes each piece of evidence to produce a conclusion by itself. Okay? So in a sense, it can do one short learning already. One piece of evidence gives you a conclusion, even though the confidence is low. If you have more, you get a whole bunch of confidence conclusion which can be merged together in this way. So confidence will become higher and higher and higher. Frequency, you don't know. If you get positive evidence, it will go up. If you get negative evidence, it will go down.
So, thanks. So, sounds to me it's a sum of the two numbers in one column, and then you times two out of 3. That's how you got the third row?
Sort of, but the real thing, the real formula is in my publication is derived from these two relationships plus how truth value, that is frequency and confidence, are defined in terms of weight of evidence. Okay, it's not that simple. It's not simple as simple as what you said, but it's intuitively speaking, it's related to that.
Yeah, because it's 2 incidents out of the next one.
Yes.
You may encounter, and that's 2 out of 3.
Yes.
Okay.
Yes.
Now,
So this is kind of like 2 out of 3. This is kind of like 3 out of 4, but not exactly because those 3 are not perfect 3. So you'll have a discount because of.
71 is two-thirds of 107, right? So
Not really. We don't have the time for that kind of discussion. But yeah, the intuitive idea is to do that.
got it.
Yeah.
But I guess just try to make sure I understand. So what exactly does confidence mean here? It sounds to me it is definitely at least a qualitative expression. But for example, if I have a confidence of 71 versus confidence of 75, do they really compare?
Yeah,
They do?
yeah, 75 means you have more evidence. Bigger number means more evidence by definition. Always.
But evidence is defined by the confidence, which is n over n plus 1. That's sort of a different weight or different scale, right? When you
Yes. Well, in terms of, yeah, it's not a probability value.
right, they don't increase at the same rate or something. Maybe there's a cross point, you know. Even this amount of counter is going up, but
Yeah, we can discuss that later.
okay.
Okay, yeah, and really have a lot of stuff after that. So this is just to give you some flavor about the inference rule in the system. Okay, so roughly speaking, there's something called local inference rule, like a revision, and also there is a choice rule, which I don't have the time to tell you. Those rules manipulate the existing belief. It doesn't produce anything new. Then you have forward inference, that's like deduction, induction, abduction. I show you, actually build a new relationship according to given relationship with a truth value abstraction. And also those rules can be used to do backward inference. That is, one of the premise is a question. Okay, you derive from a question and a belief to a new question, a derived question. Okay. Again, I'm going to skip the details. So all those things are in the system. So that's kind of like a very highly simplified version of the logic part in its core. Okay. So when you implement that into the system, you have a memory, and the memory structure include, I'm running out of the time, so I'm going to skip to a graphical representation. Okay, so at this level, the memory is nothing but a directed, weighted graph, where each node is a term, each link is a statement. And there are two numbers attached, that's the truth value I just mentioned. So you have stronger relation, you have weaker relation. You have positive relation, you have negative relation. Why I have red links and white links? White links are what I call the beliefs. That's kind of like background knowledge sitting there. And the red links are the one I call the task. That's what the system is working on at the moment. A task can be a piece of new knowledge, like this one. The bottom one is kind of, I'm just telling the system that swan is a type of bird with this kind of belief. You'll see what makes this system different from many other systems is whenever you tell it a piece of new information, it does not just put it into memory. No, it will do simultaneous forward inference. To say, okay, you tell me this, and I already know this. And if I take this one and this one as premise, what I'm going to build? Well, I'm going to build a new link here. And if I take this link and this link, I'm going to build a new link here. And you may say, oh, that's too many combinations. Well, we will worry about that later, okay? Just the memory structure is something like this. How about this one? Here, the truth value is a question mark, which means it's a question. I'm asking the system to tell me how strong this relationship should be, or whether Robin swim or not. So that's the question. So the beliefs are just given knowledge, and the task can either be a new knowledge or a question to be answered at this level. So this green circle here is what I call a concept. Now, is a concept is what? It's named by a term. So this is a concept bird. What's the content? Just what I just said. The meaning of the concept bird are not the birds in the world. It's what the system knows about that term. Okay? The system currently knows that the swan is a type of bird, crow is a type of bird, a gull is a type of bird, and bird can swim to a certain degree. That's what bird means to the system at the moment. Okay? When the system is running, as you can guess, the new links add into the system, and also the inference will produce new links. So So that's why meaning change over time. And truth value also may change if you get new evidence for certain relationship. So the overall architecture of the system, a highly simplified picture, is the input in a simplified form is you just give it new knowledge or new questions, and they go into a buffer. And this box is a selection mechanism. The same thing happened here and here and here. And at the moment we should mention this insufficient resource restriction. Okay? The system has no way to think about everything. So it will always selectively process its tasks. So some of the input, all the input will go into the buffer, but only some of them will be selected from the buffer to go into the memory. This memory is just the directed graph, weighted graph I just mentioned. Okay? And also at each inference cycle, only 2 of them will be selected from the memory. And also according to this syllogistic manner of the system, we know that these 2 relations must share a common term. Otherwise nothing can be derived. Okay? So they will be put into the inference engine, which is nothing but a bunch of rules I just mentioned, which will derive one or more than one conclusion, which will go back into the buffer. And then finish our cycle. And then we'll do it again. And some of the conclusions in the buffer will be sent to the user as output. Again, not all of them. So that's kind of like the big picture. Now you see the control strategy is nothing but selections. So in each step, I said, you select a task, which is the red link you want to process. When I say process, it means that you're going to pick a white link, which is a piece of background knowledge. And there are several different possibilities. Okay? Maybe this red link is a question, this white link happens to be an answer, then perfect, you get an answer. Okay? Maybe these 2 beliefs, and you may get a new belief. Maybe there are contradictions, then you get a revised belief, and so on. You see, this is data-driven. Okay, what process a task obtained in each step is completely determined by which belief happened to be selected at that moment. So how the selections are done? In one word, is probabilistically. That is, everything gets a chance to be selected, but not the same chance. So there is a priority distribution maintained among the concepts and within a concept among the tasks and beliefs. Everyone gets a chance, but not the same chance. So now you'll see, everything will be actually determined by the priority distribution. How to determine that? Well, that's a very long story, okay? Priority actually is a number which summarizes several factors. Who are really interested can later talk to our team and we can show you the code. But now we can tell you that the major factors, there are 3 groups. One group is the quality of the data involved. For example, everything else being the same. A high confidence statement have a higher priority than a low confidence statement. Right? A high confidence statement is kind of like what we call a fact. A low confidence statement is more like what we call a guess. Okay? If you have limited time, better use the facts than the guesses. But if you really have nothing better to do, of course you can think about the guesses. So that's one factor. Another factor is the usefulness in history. It's kind of like a reinforcement learning, but not exactly. Okay, each time you use something and it turns out to be useful for this moment, then you give it a reward, so the priority will become higher, and next time it's more likely to be used again. Okay, if it's not that useful, you give it a small punishment, so it will go down a little bit, something like that. And also, finally, it's relevant to the current context. Here, the contexts are actually defined eventually by the given or the input task. For example, if I ask the system a question, all those concepts that directly appear in those questions will be activated, which means priority will be increased. So we'll get a bigger chance to be selected to be processed in the next moment. Even though it's not deterministic, it's probabilistic. Again, there are a lot of details here in this sentence, but we don't have the time for that. Okay? Also, my talk is restricted by insufficient resource, so they have things like that. At least I'm self-consistent. So one important result is task processing will not follow a given algorithm. Why? Because it depends on many factors. Those factors change from moment to moment and in a non-repeatable manner. Okay? So, for example, if I ask the system a question, whether a bird can swim or not, what's the answer? I have no idea. As a designer of the system, I have absolutely no idea because it depends on the system's experience. Okay? What I have told the system before about birds and swimmers, and also depend on the system's resource distribution at the moment, whether the system have enough time to think about that question or how deep that thinking process will go. And also it depends on what I have asked the system before and after that question. Okay? Because if I ask the system question after that, I immediately give it another task with a much higher priority. Guess what? The previous question will be simply ignored by the system. It doesn't have the time. Okay? So what's the algorithm? At the task level, you don't have it. But it doesn't mean the system is driven by magic, of course not. Every single step, all the inference rules are nothing but algorithms. But how those algorithms are combined together to solve a problem that change from moment to moment. So you don't have a stable or repeatable algorithm at the task processing level at all. No? Also, it doesn't make sense to talk about the computational complexity with respect to a given task. Okay. That change a lot of things in theoretical discussion. Again, we don't have the time, so I have to quickly finish. So what we have described is basically this bottom part of the whole NARS system. That is, well, you may think, yeah, it sounds interesting, but way too simple. Yes, that's indeed the case. Okay, the system was conceptually introduced level by level. In each level or layer, what we are doing is we extend the grammar, we add more inference rules. And also in each layer, we are actually building two logic. First is what I call an inheritance logic, which is a binary logic, which ignores the restriction in knowledge and resource, just like what I did before. I define a binary two-threaded. Okay? Then what? Then I put the resource and the knowledge restriction into account, say, no, actually truth is a matter of degree. Then what I get is what I call a non-axiomatic logic. Okay? Then I'm going to build it more and more and more and more complicated, and then in each layer I'm going to extend it into the non-axiomatic version. So eventually the whole system consists of 9 layers according to my current design. But when you implement them, you only implement the non-axiomatic part, and this part is basically your idealization when you build the system. And also all together. So in the code, you typically don't see levels at all. They're all implemented together. The current situation is, well, later Patrick will tell you more. Basically, we have implemented most of the rules to level 8. And the top level, level 9, they already have something there, but it's not finished. Because of the time, what I have discussed is the core, and for the others, I'm going to discuss them as 3 groups. Very briefly, just tell you what each group does, how the logic is extended without any detail. Okay, we don't have the time. So the first group is level 2, 3, and 4. What I do here is to introduce more copulars. Of course, you cannot just use A is a type of B for everything. Okay? Here the idea comes from set theory. Even though a term is not a set, but some terms can be sets. So based on the ideas borrowed from set theory, we can define new copulars as variants of inheritance copular. For example, we can define similarity with this symmetric inheritance. Yes. Inheritance is one way, similarity 2 way. Okay? And also instance and property, we will allow proper name. And property is more like attributes or adjectives. Okay? They have some difference between them and nouns in terms of what kind of reasoning about. So we introduce those things. And more interesting stuff is we introduce the concept of compound term. You see, Aristotle logic has been criticized on many aspects. One aspect is expressing power. It's too simple. Okay? You cannot just have a subject and predicate. But if you think about natural language, many sentences can be analyzed into subject and predicate, except the subject and predicate is not a single word, but a phrase with the internal structure in it. Okay? This is the same thing we're doing. So we still use subject and predicate sentence, except the subject and predicate can have structures, can be very, very complicated, can be recursively defined. So the compounds here, I said we can have sets, we can have intersections of sets, we can have difference of sets, we can have Cartesian products and image. Using those things, we can actually represent the arbitrary relation. You see, in set theory, arbitrary relation is nothing but a set of pairs or tuples. Right? If you can allow a tuple be used as a single term with internal structure, of course you can represent any set, any relation in this subject-predicate format. Again, we have details if you're interested. So we have new inference rules to handle those new structures. For example, we have comparison, we have analogy. If two things are similar to a degree, then if you can say something about one, you can say the same thing about the other to a certain degree, and so on. Okay, you can guess what's happening here. It's very similar to what we said before. Also, the system not only built new links between nodes, it can actually create new nodes, given this mechanism. But the new nodes are not coming from nowhere. They're constructions of existing nodes. And system try to kind of like comprise the information. So if you know two properties often come together, then I will build a new node which can represent the intersection of them, so that in the future I will just mention that thing. So that makes sense. So that's the type of stuff we can do. And after those levels, we have a more complicated model of a concept in the system. For example, we can say every concept in the system is fluid in the sense that its meaning is determined is neither by reference to a object in the world or a definition, but by its experience relations with other things. With reference and definition, later we'll see, they will still be allowed, but they are special case or extreme case. In general, it's determined by relationship. And also the relationship, each of them is true to a degree. Not only that, meaning changes. For example, this idea is not really new, okay? The meaning of a concept is determined by the relation with other concepts. Yeah, many people have said that. but it's never practical. Why? Because in principle, every concept is related to all the other concepts, or a million of them. Okay? If that's the case, when you use one of them, how can you take the other million into account? You can never do that. But in this system, it's not a problem because at the very beginning, we already assumed we don't have the time for that. Okay? So for example, when you mention bird, the system may only have the time to think about 5 relations about birds. And that 5 relation actually will determine what bird means to this system at this moment. And when situation change, then the next time you mention bird, the system may take 3 other links. So that's a change in meaning. But it's not an arbitrary or random change. It's driven completely by history and experience or context. Okay. So it brings up many interesting things about how a concept changes meaning, where new concepts come from, and so on. So that's the first group, level 2 to 4. Level 5 and 6 is what we call higher order reasoning. Here, the idea basically comes from propositional logic and predicate logic. I have already said that they are bad, but there's some good idea we still want to use. Okay? So here, the first idea is we are going to treat a statement as a term. So we can have statements about statements. So that's where higher order reasoning comes. Okay? So between statements, we can also have a copular. Here, the 2 copular we use, one is implication. It's kind of if, then, or what can be derived from what. Equivalence, which is if and only if. Okay. So we define them formally, and we define compound statements. You see at the end, this is just from propositional logic. Negation, conjunction, disjunction, but they're defined differently. They're not defined by truth table anymore. Okay. Again, I don't have the time for detail, but it still shares some intuition. It's not completely different intuitively, but the formal definitions are different. We also have conditional implication, conditional inference as implication. And also we allow variable terms. It's kind of like universal, qualified variable, and existential variable, that kind of thing. We have something like that. We call them symbols, which can be used to represent other terms in the system. So with this 2 level, we say that this non-axiomatic logic actually can be used as a meta logic of arbitrary order logic. Because, for example, we are trying to do natural language processing by represent words, phrase, and sentence of another language, which can either be natural language or artificial language, as terms in this system. And we can also represent the inference rules of another logic as implication statements in the system. In this way, we can do natural language processing. Now we are, of course, only at the very beginning of those experiments, which is very different from the current NLP approach. Also, we can do mathematical reasoning. I have been saying that there's no absolute truth, and some people may ask me, how about 1 + 1 = 2? Is that absolutely true? Yeah, it's true in a subsystem, in number theory. It's a subsystem in this system. So the system as a whole is not axiomatic, is not mathematical theorem proving, but it can handle that kind of mathematical reasoning as a subsystem. Okay. Again, also I said truth value is not probability theory, but we can teach the system probability theory. Okay. But of course, it's not built in. It may learn it wrong, it may get it wrong. That's quite common, just like how we learn math. But it can be done. And finally, the top layer, the one that we work on in recent years, level 7, 8, and 9, that's about procedural reasoning. You'll see that previously, until level 6, what we have is a question answering system. Okay? But here we begin to borrow ideas from logic programming. That is, we give some statement a procedural interpretation. Say, they not only represent a relationship, they represent something the system does. First, we introduce the concept of event. Those events are statements with temporal relations, that is, something is true in a certain moment. Okay? For example, the door was open, now is closed. Will be open again. Okay? So now you have tense, you have temporal order among your statements, especially you have sequential and parallel order. And then we define operations which are events, but not just observed, but executed. For example, I can raise this table, this cup. Okay? But currently I cannot open the door, but I can explain or describe the opening of the door. And that thing is an event. This thing is an operation to me, but it's an event to you. You have no control, but you see the change. Okay? And if you control the change, that's an operation. But since operations or events are nothing but special type of statements, we can use all the inference rules we covered to do reasoning about them. Okay? In that aspect, there is no difference. And also, this part is how we are going to handle sensory motor in this system. That is, we don't have anything built in, but we can allow something to be plugged into it. Say that we can send a robot a command as an operation. Say, do this, and do this means move the arm of the robot in a certain direction. Okay? The execution itself may be carried out outside the system, but the system will represent it and reasoning about it is operation. That's again, there are a lot of details we haven't really used it in a robot except in some primary experiments, but that's the plan. And finally, not finally, but at this level, we also introduce goals. Goals are also something can be reasoned about. It's an event to be realized. Say, I want the door to be open. And that's my goal. Then I need to think about, okay, for that to happen, what can I do? Well, I can work there and open it, or I can ask some people I know in the audience to do it for me if they, actually do it, and then it will happen, and so on. Okay. So this part is clearly the idea comes from logic programming, but the major difference is in logic programming, everything is binary deduction. In this logic, clearly, it's not that anymore. Okay, everything is to a degree, but the idea can still be used. That is, you can use reasoning to handle action. And finally, this is level 9, what we are working on. There are special type of operations, which is not like this or that. It's operation working within the system. That's what we call mental operation. Okay? For example, I already said, you accumulate evidence, then your confidence becomes higher and higher and higher. What if at a certain moment I told you that all evidence you see are not real evidence, have been manipulated by someone else that's actually fake, you actually know nothing at all about that thing. Here we have a mental operator, which you can tell yourself, okay, everything I have seen from that channel or everything I have heard from that guy doesn't count. Okay, you can do that kind of thing to yourself. To a degree, of course. So that's something we're working on right now. So this will allow the system to do what? It will allow the system to work as an agent in the sense that it's not just do question answering anymore. It can actually change the world and itself. It can achieve some goals by execute some operations. It can do cultural inference in a certain sense. Actually, last year, we had a paper presented talking about cultural inference in NARS. It can do prediction about the future. It can explain things happen according to what should have been the case in the past. Of course, there's no absolute truth, prediction can be wrong, but that's your best guess according to your knowledge, blah, 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 blah. It can do planning, it can do skill acquisition, it can, in a sense, do self-programming, not in the sense of change its own source code. We don't think that's a good idea. Instead, by reorder its operations when trying to achieve a certain goal. Okay? To us, that's the meaningful interpretation of self-programming that can be done. And to a certain level, a certain extent, it have self-awareness and self-control. Like, for example, you can ask the system what you have just done, how you did that thing, what is good, what is bad. Well, of course, it doesn't really know that much, but a certain level, it can. There's sensor and motors with respect to the inner environment as well as to the outside. Okay, it can do inference to both of them. So a certain level of self-control. And emotion and feeling, actually, they have a paper to be presented in Tuesday exactly on this topic, so I'm not going to talk about it today. So what makes this different from many other AGI systems is they have tried to unify everything. Okay? Those of you who are here this morning in Ben Gozov's talk, you may remember that they mentioned that. They have been arguing this for about 18 years. His approach is to integrate a lot of different things. My approach from the very beginning is try to do everything use one technique, which sounds crazy, but I hope I can convince you, okay, it's not that crazy. For example, this whole system is based on the same assumption of insufficient knowledge and resource. And they use a unified representation language for everything. And it has complete inferential power. In what sense, according to my definition, just basically the idea of completeness here means whatever the system can express can be derived by the system itself. Okay? Its expressing power equal to its inferential power. Meaning that in current AI system, very often there's some knowledge you can only build it into the system. You cannot expect the system to derive that thing by itself. In NARS, whatever you can teach it, you can put into it from user interface, it should be able to derive by itself, given proper experience. And also, you see everything is unified into this concept of reasoning, but this reasoning has been extended far away from the normal usage of AI. I have another paper to be presented in Monday. It's talking about how to do learning as reasoning in NARS. Again, I'm going to skip that topic. Actually, many other things traditionally taken to be a separate process. In NARS, they're all implemented all together by the same process. You can call it learning, you can call it planning, you can call it perceiving, problem solving, decision making, or many other names. They're just different aspects of the same process. Okay. That's also my belief about human thinking. Yeah, we do have different names, but it doesn't mean they have separate process in the system. Well, do you mean your reasoning is everything? Well, of course we can use other technology, but they're all secondary. They can be used as tools, like I already said. Okay? We can plug in something as for sensation, for action, or we can call a software for a certain goal. I can use all kinds of tools for the system, but they're not part of the system. Okay? They're taken to be tools in toolbox. So anyway, that's our approach. Implementation, Patrick will say more. The project has become open source for several years. Now all the source code, the documentation are not complicated or fully documented, but quite some documentation online. We have working examples, but not to the level of practical application. but as, mostly as proof of concept. Okay, just show you this thing can be done. Even though, yes, of course, there are a lot of details to be fixed. And there are many, the system show many human-like properties. We don't have the time to go through. But on the other hand, it's not a psychological model. Okay? We're not trying to simulate human mind to all the details or pass the Turing test, which I don't think is the right goal for us. Potential application. This thing is not designed as a product for any practical application. But on the other hand, there is a possibility that some of the idea can be used to be customized into some practical application, which we are currently experimenting with several calculators. Suitable domains will typically be domains where the insufficiency of knowledge and resource cannot be ignored. You see that I'm not claiming that this NARS is a solution for all problems, not at all. If for a problem you really have sufficient knowledge and resource, which is possible, you don't use this. Okay, this is way too complicated, unnecessary. It's only when the uncertainty, the ignorance, the confliction, and so on cannot be ignored, or traditional model cannot be used because of those reasons, then you should think about this model, or something like that. And of course, we want the task to be naturally represented reasoning. And the tools can be used, use this compatible interface, and so on. And for the others, more details, as I said, many other things are online. And we welcome all possible participations and cooperations. That's all for me. Then it's Patrick's turn to show you our new version which was released just yesterday, just for this conference.
Okay, so we will proceed with the implementation, and I will show you a tutorial how to use the system, how to try on things with it, and here we go. If the system is started, this user interface shows up, and this user interface serves multiple purposes. One purpose is to be able to input statements into the system. Another purpose is to see the entire system state in a single visualization, which made it for us a lot easier to see potential issues and problems. And so, let's start here at the top. At the top we see the little user interface, which is for different purposes, like starting the inferencer, stopping it, applying single steps, changing the speed of the reasoner, resetting it, saving the entire system state to a file, loading that file, and then some user interface specific functions like inverting the color, then a priority threshold. This one I will show you later. when this one is used, and further details can be shown when this button is pressed. So the buttons above are following with the user, which is very handy, like you will see. Here you see a diagram of the entire implementation. And this diagram shows all the different actors which were needed in order to implement this system. And these actors play different roles. Like it should be able for concepts to form, for new tasks, for new statements to enter into the system, so that so the tasks can be created based on this new statements, and that concepts can be created based on them, and the tasks entered into the task bags in the concept. And the reason why we went for such an actor-based design is that NARS is in principle very nicely distributable, because the concepts in the system act as own local processing units in the system, in the memory of the system. And so let's give an example for this. Let's say the penguin is a bird. So we send this to the reasoner, and we see what's happened. At first it went to the sentence parser. The sentence parser sent it to the task creator, which created a task for it. And then the task dispatcher dispatched this task into memory. And what we ended with can be seen on the other side. There's now a concept for bird, a concept for penguin, and a concept for what we entered. The penguin is a bird. What we see here is that also our input task made it into the concept. Here we see the entire task back visualized, and currently there's just one task in it. So this is, if you try on experiments, you can easily show, if you enter, you can easily see if an input statement is still in the back, because it can be that the system derived new knowledge and decided that there is something more important than what you input can happen. And here you can check what is really still in the concept. And to go back to our example, to show how we can reasoning, how the system can apply reasoning now. There's an output rectangle, and this output rectangle, you see what's happened so far. We input a statement that penguin is a bird. And it's entered a default confidence value for it, and it has a frequency of 1 because there is only positive evidence. If we now say that bird is an animal, and we send this, now we have two tasks. Penguin is a bird, and bird is an animal. And if we now apply the step button at the top, we will see that the system begins to derive new knowledge from what it got so far. Here we see that the system began to believe that the penguin is an animal. This was applying the deduction rule on our input. More interesting for many people are cases like the abduction rule. Let's reset it. And let's say, for example, that dim is an instance. This is why we write it this way. because it cannot be further specialized. So if we say, for example, dim quacks, and we say additionally duck quacks, then we see a first use case for the abduction work. Send this to the system. Oh, I clicked too often, but here we go. It believes that duck. Oh, this was not the conclusion I searched for. This one is it. It believes that dim is a duck because dim also quacks. The duck quacks, dim quacks, so dim might be a duck. So it already has found a certain pattern in its experience and has used this pattern to derive new knowledge. And so what we saw so far is how to enter statements into the system and how to derive, let the system derive new things. Where to proceed? So if we go back to the concept graph, now there are already a lot of concepts, and nearly all of them are not directly our input statements, but concepts which were derived from our input statements. And this is one nice property of the system, that it begins to create concepts which summarizes its experience. And here you can also see that the semantic, that the concepts are usually connected based on the semantic relationship. For example, duck quacks is fully connected to the concept duck. There is also the possibility to filter concepts. If we go to this concept back window and enter duck, now it will only show us concepts which are related to duck. And so we can filter this concept graph for different things we are interested in, which also makes it much more easier to see what knowledge, what derived knowledge does the system have about a certain topic, and about a certain term. Additionally, there is a priority threshold option on the top of the graphical user interface, and this does the following. The concepts, as Pei already said, they don't have same priority, but which concepts currently have a high priority depends on the current context. And so they are all ranked. They are ranked in the back, have different priorities. And if we are, for example, only interested in the concepts which have a certain priority, then we can increase this priority threshold value, and it will begin to only show us the concepts where the system thinks currently that they are more important. Right. So this gives a nice way to see whether the concepts one expects to be important for the system, if the system also thinks so, if there are other concepts that evaluates as more important currently, can be nicely evaluated with this concept graph. Another thing which you might see here, there is a link. I don't think this is necessarily visible, but there's one link. There's the concept dim, and this concept dim is, in this case, okay, let's choose another one. My point is, concepts link to each other but not necessarily with the same link strength. So it can be that a certain concept prefers to interact with another, while the other one does not prefer to interact with the first one. And this has multiple reasons why this is a good idea. The best aspect about it is attention related, because attention should be directed. And so this, what we already see here is that the system directed relationships between concepts. And as we also discussed, because of the assumption of insufficient knowledge and resource, it is the case that a concept, it can't have arbitrary amount of links. It has to choose which other concept it decides to interact with, based on multiple criteria, like was did the interaction with the other concept lead to an relevant result, to an important result, or result of high quality, and everything this is concerned handled. Next thing, I can show you an interesting decision-making task, because for me personally, the question answering is already nice, but it's even better to have the system to apply creative decision-making in order to find a solution to a problem. And this is especially interesting with the system because the system might not know a lot about certain coherences it has to use, and so has to try different options, and we will see one of these examples. And it's called the toothbrush example. I just want to scroll because I don't want to show you the entire solution already. Let's say we know some pieces of knowledge already, like that a toothbrush is made of plastic, that hardened objects in the right shape might be able to unscrew our screw, that plastic can be melted, that if something is melted, it is pliable, that heat causes things to melt. So different pieces of knowledge. Here, in this example, we assume that the system already has certain opinions on different relations for objects. And the question is, for the system, it should unscrew the screw with the options it has available. And there are different options it can use. And in the end, the system should, by reasoning, apply the decision-making process, which looks as follows. At first, the toothbrush, which is made of plastic and can be melted. Probably it makes sense to use the lighter, which generates heat in order to melt the toothbrush. Since the toothbrush then is pliable, it can then be reshaped. So the system then has to reshape it and let it cool in order to be finally able to unscrew the screw. So this is also interesting. It also compares to some animal experiments where the animal has to use certain steps in order, some creative steps, and has to find out how to get food, for example. And we can simulate this example with the system. I won't go into the details here. So this is also one part of the user interface. If one has examples like in a text file, it's possible to just copy it, and then when the paste button above is pressed, it will automatically input whatever is in the copy-paste buffer. So we paste it now, and the system will begin to try to solve this problem. We will also set it to fast mode, in order to be a bit more effective here. And it begins. The system, we can see, for example, we can filter the output for toothbrush in order to see what the system reasons currently about it. It was probably already too fast because it already, let's slow it down, I stopped it. It already derived that the toothbrush might be the solution to the problem, that the toothbrush, that it should somehow make the toothbrush playable, and that it should, after it's playable, reshape it in order to be able to reshape it into a form with which it can open the screw, unscrew it. And it was already pretty fast. Didn't expect this, because sometimes it takes longer. And what we soon will see, it's still thinking a lot about the toothbrush, as we see here. Constantly new tasks arriving, derived tasks, but I think it already did it. Oh, in fact, it already did both things. It applied the lighter to the toothbrush in order to melt it, and then applied the reshape operation to the toothbrush, because it thinks if it is reshaped, it might help it to unscrew the screw. So it has successfully applied, has successfully achieved this decision-making problem. This is actually the one which was suggested by relational frame theory, which is also a nice example, because the system, we didn't need to adapt it for it. The knowledge which was represented in this example was easy to represent in the non-axiomatic logic, and this was everything for the system in order to deal with this example. And this is what we have. Another thing, because there still seem to be 10 minutes left, is this right?
Yeah.
I think so. Then we can also try a normal question answering example. And there we have some interesting domain, and it's detective domain. Imagine you are a detective, and there are multiple people claiming different things, and you have to decide who is the murderer. And you have to summarize the different evidences you get from different people, and you have to judge on your own. And often this is also a nice example which shows that in the real world you are often challenged by conflicting evidence. If one person says this and the other person says the opposite, we won't go crazy, we will summarize this experience and work with it. And this is also what's happening here. Here the detective gets multiple informations, like the dim lives in Graz, the dim lives in Graz, and another person says, no, this is not even the case. Another one has some subjective judgment and says, people with sunglasses tend to be aggressive. And another person says, aggressive people tend to be murderers. And one says, I know, that Tom owns sunglasses. And the system now has multiple evidence, and we can ask it, what do you think is the murder? And it summarizes all these different evidences. Let's reset it. But before, let's have one look at the graph, because it will, it's currently, does it not visualizing? Doesn't matter. Let's reset. Let's go for this detective example. Copy. But at first we will filter the output for answers, and this is possible by just typing answer, because answers are marked as answers. So we will filter the output because we are only interested in the answers. And let's ask the system who it thinks it is, who it thinks that the murder is. Let's go to slow mode. Slow mode. Oh, the system is started, or the things were going in. In case that you wonder why there are exceptions, it's because of the comments, because those are not NARS statements. Those are not NARS statements. So, the system, probably it's more interesting to see what derives. Here derived a question answering who is not the murderer. We asked it who is the murderer, and the system derived who is not the murderer. And this case should probably not. Then here it says, here it derived if Dom on some sunglasses, and if somebody on sunglasses is aggressive, then also it derived that Dom might be aggressive because of this, that he owns sunglasses. And so it's deriving a lot of things based on this, what we entered. And yes, important, if we are only interested for the answer, then the best thing is to just set the system to fast mode and let's see what happens. Here we go. At first it said that dim is, okay, it's probably saying, it's essentially saying it has equally amount of evidence that dim is the murder as it has that dim is not the murder, which is right, because one person claimed that dim is the murder and another person claimed he is not, and it also already found the most confident answer it can receive, can find out in this example, and this is that Dom is the murder. And this is also what it says. And so often what we also see here, because of the assumption of insufficient knowledge and resource, the system can never know when it found a first answer that this answer is the absolute answer, and it does not have to find for another solutions, search for another solutions. The system will probably decrease the priority of this question when it was already satisfied to some degree, but it will still continue to search for better answers. If the current context makes the system, drives the system in doing other things, it will probably forget this question. But if it has nothing different to do, like in our example now, it happened also here now, it searched for the best answer it can get, and this is what happened. It searched for another answer and came up with this other solution of higher confidence. So the system can be used to question?
Yeah, can the system take in new evidence while it is reasoning? So you were doing the steps, so supposing new evidence comes in that would increase the confidence of him being the murderer, would it take into consideration and provide an answer?
Mm-hmm.
Or rather change its confidence?
Exactly, this is happening. Let's continue the system. So as you see, it's currently reasoning because it's running, but we are filtering for answers, and while it is running, system is going, we say no. Or we say Dom is not the murderer. In case that it hasn't forgotten the question, it would have answered, but it looks like it forgot it, so we will just ask it again, who is the murderer? And we see that it updated and says, no, Dom is not the murderer. It's not saying that he is not the murderer at all, because it still has the positive evidence it found before, but input usually has a high default confidence, so it tends to say, no, he's not a murderer. The more evidence it collects, the more stable will this become, and the more difficult it will become to convince the system otherwise.
So do you have a large database, a large knowledge base? How big a knowledge base have you built in this system?
What we see here, and this example was really only this what we entered. So this example file. So it started with zero knowledge, and I entered those statements and it derived further knowledge from it.
Right, but at your lab, have you built a significant size, common sense database like the psych database to work with?
We have tried some small, not in the scale of psych, but should be here somewhere. We have tried to encode some everyday facts and see whether the system can come up with good conclusions. And the thing is, one interesting part of learning, truth alone is not the entire story. It also has to learn what concepts are important in what context. And this makes it for the system often difficult if you enter a lot of statements to judge in what direction it should think. Well, if a question is entered or a goal is related to it, it's much easier for the system to direct its attention to the right statements. So it's very attention driven. Attention is really the core aspect of the control mechanism behind the system.
I mean, one of the large scale ones we've done is WordNet. We've put into the system by applying truth values to WordNet. But it's relatively easy to add existing databases. There's a lot of resource on the internet, so we haven't really focused on that because it's not been an issue. But in terms of scalability, we've run the system with 3 million concepts, but not necessarily from a large ontology, but just to scale the system to get a feel for what it's capable of. So I don't know if that is getting to the root of your question, but it's certainly scalable, and we have done tests on larger data sets like WordNet. But we don't have an existing NAL-based database as such. But as you can see, it's very, very straightforward for the system to generate huge amounts of data from very small input sets. And all of that will be logically sensible information that is perfectly valid data. So that is not an issue for us.
Right.
So you had mentioned earlier that the system's adaptable. When it gets new information, is there a mechanism to make previous or later information more important than stuff that happened very far in the past?
This is one thing, just forgetting applied to tasks in the system, so it will tend to give new items a higher priority. But it often depends on context. It can be that something is important which happened in the past. It depends on different contextual criteria. So sometimes future task may be important, sometimes a past task, but there's a tendency for prioritizing currently happening tasks as higher. This is due to this forgetting mechanism.
I have to interrupt. Can you just show people how to download the code? Where to download the code?
Oh, yeah. And there was one question, probably you can ask it in parallel.
So I was going to ask, is there what kind of way would you model like authority into it? So like, if the person inputting the data, whether or not they're reliable, whether or not they're lying to you or something like that. Because I've seen a lot of people use non-axiomatic systems to like, and they would lie to like a game character about the rules of the game, and then the game character would go act on it, and then it would discover in the world that it was lied to, and it would react to that, by
This is a difficult issue. The best thing the system in principle can do is relying on its own experience, and if all this experience is produced by layers, then the system can't do much. Well, when most of its experience comes from independent sources, and there are just some people who give false information, the system will just summarize it, and the other information will win over the new one, which is produced by layers. So it depends on if the entire experience the system has is wrong in that sense, the system can't know. It can apply mental operators and try to find criteria when people are trustable and when not, but this is a future story.
Yeah, I mean, it's part of the bigger picture of education. So, I mean, if you're being taught absolute rubbish from an early age, then you're just going to grow up knowing absolute rubbish. I mean, there is no solution to that, and you have to be taught sensibly. There can be conflictions in that teaching syllabus, but it generally has to make logical sense, otherwise you're going to grow up with nonsense. It's the same issue.
Yeah, I know there must be many more questions, but we're running out of time. But tomorrow evening in the demo session, NARS team is going to participate in the demo session. So we have 2 more hours to actually go through examples step by step. Whoever are interested, you should show up tomorrow evening, 6 p.m. to the demo session. Okay. Also, for the rest of the 3 days, our whole team will be, glad to answer all kinds of questions. Today, we will just have to stop here. We are going to stay a little bit longer, so if anyone cannot wait until tomorrow, you're welcome to ask us. But I'm not going to hold everyone else here. So thank you for coming. Thank you.